Welcome to the final lecture. Remember that PS12 is due on Monday, that's April 20th, or with late days on Wednesday. The help schedule will continue as usual through Tuesday, April 21st. There'll be a modified schedule on Wednesday, and then the regular schedule will stop. After that point, if you'd like to contact me with questions, feel free to do so on Piazza. The 3 Caddis problems that make up the final are due on Wednesday, May 6th. That's a hard deadline because I have to have time to post the grades. The video that follows is from 2018. It deals with our continued discussion of ways of coping with NP completeness.
Problem version, equivalent of backtracking is branch and bound. So here we got to, if you take out the bound part, just have the branch. It's like the recursive backtracking, except when you find a solution, you still got to back out and try the other way. You're just looking for the best answer. So I couldn't think of a better example to illustrate this than Traveling Salesman Problem. So here, you're welcome to. I haven't posted it yet, but I will. Here's a starting point for the Caddis problem. Okay? Part of my trying to make things easier here in the last week. So let me explain how my TSP algorithm works. So again, I'm using statics for a lot of the parameters, not all of them as you'll see. The things that don't change, I just want to avoid passing them around. So I have the number of vertices, V. I have the graph. Now notice I've used an adjacency matrix for the graph, not an adjacency list. Why is it better to use a matrix? Yeah?
Because we know that in the Traveling Salesman Problem, it's a complete graph. So
well,
every single step.
Yes. At least the version of the TSP that on Caddis, it's a complete graph, and so it's definitely as dense as it gets. So you want to use this just to speed up, speed up lookup. So. Now, the other thing, this is key in branch and bound. You're going to have the best answer you have found so far. So initially, it's infinite, effectively infinite. And what we're going to do, as our algorithm runs, as we find a better solution, we'll replace that. And gradually, that will come down. And when the method is returned back to where it was called from, that so far will contain the answer. And then this tells me, as I grow the path, I'm growing the path and trying to go back to where I started from, that set will contain the indices that we visited already, the vertices we visited already. This just reads in the graph, so I'll skip that code. First thing I do, I'm going to always start from vertex 0. It doesn't matter where you start. And you certainly don't want to, let's say you start at 0 and don't find a solution. You don't want to try starting at 1. That's not going to work. I mean, you're not going to find a solution. It doesn't matter where you start. So we'll start at vertex 0. So I add it to the visited set because we've already been there. Then I call TSP solve, and we'll see what those parameters are. And when we're done, I print out best so far. Yeah?
So there's a diagonal that runs from the top left to the top right. Are you never going to make a move down?
Yeah, the numbers on the diagonal don't matter.
So
You would never use them.
It's like a potential optimization that you don't have to like.
Well, it might. That's really small because you put them in the graph, you never look at them. So there's really no overhead except creating the graph in the first place. All right, so here's my method. So what it takes is the current vertex. So conceptually, we're building a path. So current vertex is the last vertex on the path so far. Current total is the total weight of that path from 0 to the current vertex. And current length is the number of edges. Or I don't remember if it's the number of edges or if it's the number of vertices. It's the number of edges. Number of edges on the path. So initially, the current vertex is 0. The current total is 0 because we have no edges. And the current length is 0 because we have no edges. That's why we pass 3 zeros to TSP solve. Okay? Just like with the backtracking, there's a base case. If the current length is v minus 1, the full path will have v edges. Right? So if we have v minus 1 edges, then all that's left is to go from the current vertex back to 0 to close the loop. And so what I do is, okay, the current total plus the cost of getting from the current vertex to 0 is going to be the total cost of the cycle. And so we try to update best so far. We take the min of best so far in this new thing we just found. Okay, that's the base case. Then when we return from the base case, we'll try some other, we'll make some other choice somewhere else. So this is where the recursion happens. So what we do is, we're at some vertex, and we've got to try going to other vertices. We've got to try all possibilities. So I iterate through the vertex number, 0 up to v. If I haven't yet been to that vertex, this is what the visit array is for. If we haven't been to the vertex, then we consider it. If we have already been to that vertex, we don't consider it. So we're just concerned about visited vertices here, unvisited vertices. And then what we do is, we add it to the visited. After the recursion, we remove it from the visited. So there's that theme again, about making a change and then undoing the change. We're not making copies. Vertex becomes our current vertex, the last one on the path. So conceptually, we're adding the edge from the old current vertex to this vertex that we're getting from the loop. So that's our new current vertex. Our new current total is the old current total plus the cost of that edge that we just conceptually added. We're not recording the path anywhere because we don't need it. And the current length has gone up by 1. And that's all there is to it. That's the basic. This will find, if you wait long enough, it'll solve any TSP graph. It certainly won't pass all the test cases in CAS. But it's a good starting point. Now, before we talk about making this more intelligent, in other words, we're not using branch and bound, right? We're just using branch. There's no bounding being done. Can you think of any attacks you could make on this, any ideas you could have to make it, just to make the base code faster? Yeah?
Well, we're already keeping track of best so far. So if we know our path at any point is bigger than best so far, we can abandon
Well, that's the bound part.
Okay.
So the independent of the bound part, yeah.
So, why not just iterate through the visited thing instead of having the for loop?
Okay, well, what we'd want to, all right, so that's the idea. This loop can be fairly expensive, right? If almost every vertex has been visited, we're doing this loop, and since most of the vertices are visited, the iteration is kind of a waste. So an idea might be, what if you had an unvisited set? Instead of iterating through all vertices, you just iterate through the set. Okay? Now I didn't implement that because I was thinking, okay, so you're iterating through the set. What are you going to do when you find it? So you pull the first element out of the set. What do you do?
Did your son do that?
I don't know. Okay, so just imagine if we replace this with something like for int vertex in unvisited. So imagine we had an unvisited set, and that would have to be for each. So what if we had our loop? Okay? So then we would get rid of this right here. Right? We just iterate through the unvisited vertices. What's the problem? Yeah?
You're modifying unvisited.
Right, because what we have to do is, instead of adding to visited, we would remove from unvisited, and then we'd add it back here. But now you've got a concurrent, you get an exception if you modify the set you're iterating over. So I just didn't feel like working out the details. There may be some way around it that doesn't, there's certainly a way around it if you just make a copy of the set. But I want to avoid copying the set. But it's something to think about. Okay? That would be the main way, if I were trying to think of a way to make the base code faster, that I would do. Because there's not, the rest of it's pretty stripped down. Now, notice that we have to explicitly add and remove. Add and remove. But why don't we have to do and undo the current total, or the current length? Yeah.
Because they're just passed by value to the next.
Yeah, they're just passed by value, right? So it's not like we're reassigning current length. We're just passing current length plus 1. Current length doesn't change in this stack frame. Okay? Now one thing just occurred to me is you could do something like compute current length plus 1 and store it in a temp. And then just pass the temp each time and avoid doing that addition. But I bet the compiler will, if you run in release mode. Of course, you don't get to choose that in CAS, do you? I don't know. So anyway, those are things you can try. Now, so let's copy this and go try it out. Problem here, right? Utah.tsp, that's not Java.
Pass it.
Passes all tests.
Oh yeah, if this passed all tests, you'd be happy.
It's gonna take a while because. That's like only
Have points for copy.
Okay. So it passes 5 of the. Anyway, no one needs to get a 0.
Yeah.
Okay. So let's go see if we can get the grade even higher. So what we want to do now is bounding. Yeah.
Would you recommend using a language faster than C# for this problem, or
Yeah, certainly if your program is just too slow by a factor of 2, which is hard to know, but then going from Java to C++ will definitely get you over the hump. It's not clear to me that going from C# to C++ will work. Anthony got over the hump by going from Python 3 to Python 2.
I converted my solution from C# to C++, but by a factor of 3.
By a factor of 3? All right, now take back what I said. Yeah?
C++ doesn't have current modification check, so yeah, be careful. That's true.
Say that again?
He said C++, it's like a lot of other things. C++, he said, doesn't have the concurrent modification check. So,
multiple threads don't help you pass.
so what's that?
Multiple multi-threading doesn't help you pass.
Okay, yeah, he wasn't talking about multi-thread. This was changing the thing you're iterating in the loop. And instead of giving you an exception, it just goes haywire. Yeah. I have noticed over the semester that people in C++ will have these problems, and I'll think, wow, why didn't I ever hear about this before? And the reason is, in every other language, it was an exception that got generated, and people knew something was going wrong. C++, you know, it just goes crazy. So it was definitely a trade-off here. Okay, the easiest thing in branch and bound, you really don't have to know anything about the problem, would be what? What would be the simplest bound to make? I think someone already said. What's the simplest improvement?
No, like for the remaining.
Well, even simpler than that.
Oh, it's less than, it's greater than this.
Yeah,
If you already have a best so far, check if it's already greater than that.
right. So when I come in at the top here, why don't I just say if current total is greater than or equal to best so far, there is no point in continuing, right?
Can you do it before you call it?
I could do it before I called it, but
And then use the new current total?
yeah, but I don't know. It doesn't make a huge amount of difference, and this is, you know, anyway, you're certainly welcome to make the change. See if you can improve it. So that's the basic branch and bound idea. If you already, you know, if the best so far is 100 and you're not done yet and you're at 101 or even 100, there is no point in pushing forward. There are no negative edges. If there were negative edges, it would be a different matter. So just give up. I mean, give up on this branch, try a different one. So let's see. So what did I do before? 5?
Yes.
Am I doing this wrong that I have to keep resetting this every time?
You have exit file.
But I keep having to pick the language.
you don't have to drag and drop.
You just drag the file.
Oh, okay. Anyway.
Well, What was the answer? It automatically what?
If you drag and drop, it automatically detects the language, I guess, from the file extension or something. All right, so let's see just how that simple change changes things. Okay, so we're already at 6, and I think that's as far as we're going to get.
So it's about 15. 15. 12. Well, it goes 13, 15, 17.
Okay, but just that simple change got us up one level. Okay, so that's half, right?
So calculate like a best possible from where you're at?
Okay, so let's try, well, I'll try one more because I don't want to just stand up here and do the problem for you. Okay? So we know that every edge is of weight at least 1, right? So to current total, we know we're going to, how many edges are left? Well, there's current length and there's going to be V edges. Currently there are current length edges. So we'll just add to this estimate V minus current length. Okay? So for each edge that we haven't put in, that we haven't considered yet, there remain to be V minus current edges to add. Each of them is going to be at least 1. So let's let that be the math. I'll just stick to my old ways here. I'm sure you folks are all experts at this by now.
So once we get close, we just like randomly subtract number and.
No, that's all right. So let's see. That's
I don't think it's
6.
gonna do that much better than
Yeah, I don't think it's going to be much difference. Okay? No, that's a time limit exceeded. Okay? So that wasn't enough. What's another thing you could consider there? Instead of adding 1, what'd be? Yeah?
I used to get checked what the minimum weight in the graph is, so like
Right.
it's not guaranteed to be 1.
If you knew what the minimum edge, suppose you knew the minimum edge in the graph, the weight of the minimum edge in the graph, which you could calculate once ahead of time, right? Then we could just say V minus current length times min edge weight. Okay? Which can't be, there can't be an edge less than that. What the heck? Let's try it out. So let's see what we got to do. I got to have a min edge weight. And then down here, each time I read min edge weight equals math.min of min edge weight and this thing here. Now, this isn't the world's most efficient way to do it, but I'm just in a hurry here. So.
You got to set min edge weight though, because it starts off as 0.
Thank you. Okay, see what I did there?
Yeah, I don't think you want to.
You're on one.
Got to set it to max.
It's good to have you all here.
Or you just set it to 500. It'll never be above 500.
Okay, that look good now? Of course, we can make this faster by just doing the parse once, but maybe the compiler will help us out.
Or you said you wouldn't give us any edges greater than 500, right?
Okay, yeah. Well, anyway, good enough. All right, what's the fast way to do this?
Control C, copy it, and then edit.
Whoops.
Oh, nice.
Copy it,
And then click the ID number in your try.
right here.
Yep. And it should give you it's a recent.
Problem is
It's different.
It's different because
Just hit where it says problem.
Oh, you have all the tools that you get.
Telling Salesman.
Okay, I could have had it done already. It's hard to listen to everyone making suggestions. This is the last one. Last one. All right. I have no idea. I didn't try this last night, so I don't know what it is. It'll be embarrassing. It won't be embarrassing, but it'll be sad if it solves it all. How many of you have been working on it and haven't gotten that far? So anyway, I don't want this to be a frustrating experience, you know. So you don't have to worry about. I mean, this gives you the starting point, and it's easy, as you have seen here, to experiment with doing better and better bounds. And just keep in mind that you can probably think of some really good ways, but if it's too expensive to calculate the bound, then that may not pay off. And so it often pay off. Imagine if we had to calculate the minimum edge each time we did the test instead of doing it in advance. So anything you can pre-calculate, it's going to work well. And it's going to take some ingenuity to get all the way to the end, but that's okay.
Wow. That's 8.
All right. So I'll put this online, but I'll probably forget. So I'm sure someone will remind me. Okay, now let's go back to PowerPoint. And let's look at.
It's going to be normal scoring on this last one.
On this last
grading.
one?
It's going to be normal
Yeah,
grading.
the scoring on this last one it's not sort of, it's if you get X% of the test cases, you get X% of the points. So getting close gets you close to a perfect score, unlike previous CAS problems. Okay. So this is branch and bound again. This is like the sort of the general case of branch and bound. And again, this is iterative version. We just did the recursive version. But essentially, you start with a problem like before, with backtracking. You let S be the set of active subproblems. Best so far is infinite. Now, if you're doing, sometimes you're doing a maximization problem, so there it would be negative infinity. While the set is empty, not empty, you choose some subproblem from the set. So again, that's a place you can be clever if you're doing it iteratively. If you're doing it recursively, there is a little bit of room for this choice. So what would be, we'll talk about when we get to the recursive case. But here you've got this big set. You choose the one you want to work on, whichever one you think you can figure out is most likely to pay off. Well, why does it matter which you choose first? Since you've got to try all the possibilities anyway. Why does it matter which you choose first? Yeah?
If you can set best so far well early, you can cut a lot of stuff out.
Right. If you lock on to a solution, so in this one, since the graph is complete, it's never going to fail and have to back up. It's always going to reach, unless you have the bound set, it's always going to reach a solution. So if you could find the best solution first, then your branch and bound starts working really well. It starts pruning. So it's a big payoff to get a low best case in there first.
So use a heuristic.
Well, so he asked about heuristics. The danger with heuristics are basically ways of making choices that may or may not pay off. And the problem with a pure heuristic is, a heuristic would be, I'm not even going to try this subproblem because it looks like it's not going to work out. It's not going to improve. But if you're wrong, you've missed the solution. So for this one, you don't want to use heuristics because you've got to get the right answer. Okay, so you choose which one you want to work on from the fringe of the tree, except it'll be in a priority queue. You expand into smaller subproblems. For each one, if it's a complete solution, you update best so far. If it's not a complete solution, you do the bound part. You make some estimate, and if it can possibly pay off, meaning it's still less than best so far, you keep it. Otherwise, you throw it away. And when you're all done, you return best so far. So the yellow things here are places you can apply some intelligence. Recursive branch and bound. Let me see where I'm headed. Recursive branch and bound. You start with the problem, best so far, you call optimize. If it's a complete solution, you're done. That's the base case. Right, you're not done. You're basically at the end of the recursion. So when you got a complete solution, so you've closed the loop, update best so far. Otherwise, you apply the branch and bound thing. So if it makes sense to go forward, you generate the subproblems and systematically deal with each one. Okay? So that is clearly a place where you apply intelligence. What would this correspond to?
That's,
In TSP case, you've got some subproblem, which is a partial path, partial cycle. Yeah.
that's the next vertex you want to go to that you think will be part of the
Okay.
Hamiltonian cycle.
So right here, the subprobs you generate are going to be an edge to some unvisited vertex. So there might be 5 unvisited vertices. So you consider extending the path to all 5. So you can apply some intelligence here by choosing which order you consider those vertices, maybe. You've got some reason to think going to vertex 4 is likely to lead to a better solution than going to vertex 5. You want to do that first.
So short the edges and pick them.
I mean, hard to say exactly what order. Now, we did this example last time. So if you read the book, in the chapter on this, it says one way you can improve, the way you can put a bound on traveling salesman problem is, okay, so you know the vertices that you have traversed so far. You know that you've got to hook all the unvisited vertices together in some fashion in the future. And you've got to hook the visited vertices and unvisited vertices. So essentially it was, what we described was using, at every level of recursion, computing a minimum spanning tree for the remaining unvisited vertices, which would give you a lower bound on the cost of hooking all those up. And so the bound would be the cost of the minimum spanning tree, the current length of all the edges that you've already used, and then the 2 lightest edges that lead from the visited vertices to the unvisited ones. Okay? And that's great in the abstract. I tried it out once. It failed miserably. Didn't speed things up, it slowed things down. What was the problem? Yeah.
You have to compute the minimum spanning tree at every single level.
Right, minimum spanning tree algorithm at every level of recursion. It was just too expensive. The cost of computing the bound was too high. And so even though the book talks about it, I don't recommend that as an approach. You've got to find a cheaper way to set the bound. Now, if you really want to go full out, you can try, instead of, what you want is, you can put a minimum spanning tree. So the first time in the recursion, at the first level of recursion, you're computing a minimum spanning tree for the entire graph except for the starting vertex. Then you pick an edge. You want an algorithm that will take the minimum spanning tree you just computed and compute a new one from that would be a solution for all the vertices except the one you just went to. So you need something that will let you take a minimum spanning tree and shrink it, shrink it, shrink it, shrink it as a set of vertices shrinks. An incremental algorithm. So that rather than computing it from scratch each time, you base the new minimum spanning tree on the old one. And there are algorithms for that. A little hard to dig up online. But I think your time is better spent trying to find better ways to set the bound. But anyway, we went through this animation, but it illustrated branch and bound. And you can see that, we don't generate the whole tree, things get cut off. So then the end, I'm not interested in the details right here. So that's how we solved the problem by, all these places were places where we realized that we were higher than the best solution found so far. And you could, rather than having a tree with n factorial leaf nodes, we have much more manageable number. There's the end. Okay? And other ideas for lower bound we have, there's some you can look at. See if that's all of them. Okay? So there are some things you can think about. We've talked about some things you can think about. Kick ideas around. Let's see what you come up with. It'd be nice if everyone could find a way to the end of this. Okay? Okay, so we've been talking about coping with incompleteness, and that's sort of what you're doing on this week's CAS problem. We've looked at 2 approaches. Exhaustive search using intelligent backtracking, which is a way to solve a search problem, and branch and bound for optimization problems. There are also approaches, like one approach, a lot of times you get a special, you can have an algorithm, a special case that you can solve efficiently. Sometimes you can find approximation algorithms, algorithms that will give you something that's approximately correct quickly. So I just want to show you a couple examples of these first two. That's going to involve skipping through all this stuff here. So. All right, we really haven't talked about the independent set problem much, but you remember it's an undirected, the idea is you've got an undirected graph, and you want to find the largest set of vertices that you can that are pairwise unconnected by an edge. So no two vertices are connected by an edge. So you try to just imagine coloring some of the vertices red, and you want no two red vertices to be connected by an edge, and you want to color as many red as you can. So that's an NP-complete problem. The special case in this case is if the graph is a tree. If the graph is a tree, there's a neat little dynamic programming algorithm I didn't have time to talk about. There's actually a slide back somewhere in the dynamic programming deck about it. But that's just an example of a case where the general case is no one knows a fast way to do it, but there is this special case where the graph is restricted where there is a fast way to do it. The same thing is true of shortest path. Right, in the completely general case, shortest path, where you can have negative edges and negative cycles, shortest path problem is NP-complete. But if you add a restriction that says there are no cycles of net negative cost, suddenly there's an efficient algorithm to do it. We looked at several algorithms that exploited different restrictions. But every one of the three algorithms we looked at for shortest path had a different restriction on the generality of the graph. Traveling salesman problem. That, you know what that is. It turns out there is no efficient algorithm in the general case, and no efficient approximation algorithm in the general case, unless P equals NP. But for this special case here, there is. Now let's think about it for a minute. So the traveling salesman problem is the optimization problem of trying to find the shortest cycle, the shortest Hamiltonian cycle. So what would an approximate solution look like? What would an approximation algorithm be for the traveling salesman problem? And what would it do? How would it behave? Yeah?
And just pick all the nearest neighbors until you get an
Well, yeah, I'm not looking for a definition. I'm not looking for the algorithm itself. What would it mean to come up with an approximate solution? Yeah?
It would be a cycle that might not be quite the shortest, but
Okay.
close to the shortest.
It would be, maybe you don't want to spend the time to find the shortest cycle, but the least weight cycle. But you find one that's close, one that's almost the smallest. Maybe it's in a factor of 2 or 5 or whatever. Okay? Now, how can I say that it is known that unless P equals NP, which is considered unlikely, there is no approximation algorithm, no efficient algorithm that will find even an approximate solution to the traveling salesman problem? Any takers? I'm not looking for the algorithm itself. Okay? So let's go back to the definition of the traveling salesman problem. We're trying to find the lightest weight Hamiltonian cycle. So, yeah.
That means you would be able to solve the Hamiltonian set problem?
Exactly. Even an approximate solution to the traveling salesman problem would be an exact solution to the Hamiltonian cycle problem. The Hamiltonian cycle problem is just to find a cycle. Forget the weights. Just find a cycle that visits every vertex once. So an approximate TSP solution, no matter how bad the approximation, would, at its core, be a Hamiltonian cycle. And Hamiltonian cycle by itself is NP-complete. So no matter how you define, no matter how bad an approximation you're willing to put up with, there are going to be cases where you can't even get that close, unless P equals NP. But if we put a restriction on the graph, we can't come up with an approximation algorithm. And that's what the triangle inequality is talking about. So here's a triangle inequality. It just says if you have any three vertices connected in a triangle like that, that the distance A there is less than or equal to the distance B plus the distance C. I say distance, it's just the weight. So the cost of going directly, the cost of that edge from U to V is going to be less than or equal to the cost of going to V and W. Okay? That's a triangle inequality. Now, what types of graphs will the triangle inequality hold? Yeah.
Like a regular map?
Like a map, a physical map where the distances are mileages, for example. That'd be the most common thing. Now, what's a kind of graph that it won't hold on? Yes?
The one we're trying to solve?
Well, the one you're trying to solve, certainly, where the edges are just random. Yes?
Directed graphs.
What's that?
Directed graphs.
Well, I guess in a directed graph, it may, well, that's not exactly what I had in mind. I'll just leave it at that. Yeah?
Negative weights on the
Negative weights, well, strictly speaking, you could have the triangle inequality satisfying even with the negative weights. Yeah?
The one where it doesn't follow some coordinate system? Like on
Okay.
a map, you have a set of coordinates.
Yeah, it doesn't follow some coordinate system. You're not, there's no reason you guess what I have in mind. What I have in mind is airline prices. Right? Is the price of flying from, let's say, Salt Lake to New York necessarily going to be less than or equal to the cost of flying from Salt Lake to New York via Cincinnati? I mean, there is no rhyme or reason to there isn't a rhyme or reason to airline. Sometimes just by you can find a cheap way to get somewhere by taking a more inconvenient route. Okay, so that's what I'm talking about. You got graphs that don't model physical distances, but that's an important application. UPS, FedEx, whatever, they are talking about distances when they're trying to find a short cycle. So let's see how you do this. So just imagine that we have this, and imagine this is a map, and so these are the vertices, and the distance, there's an edge between every pair of vertices that corresponds to distance on the map, physical distance. So let me show you an approximation algorithm. The idea is that we compute a minimum spanning tree first. So that can be done quickly. So I think that's the minimum spanning tree, something like that. And then what we do is we start somewhere and we construct a tour that starts, let's say here, and visits every vertex and comes back. And we construct it by following every edge twice. Let me show you what I mean. So we go from H to G, and then from G to G. Well, that's obviously a typo. We go there, we go there. There's nowhere to visit, so we go back. And then we go to the vertices. When you get stuck, you got to go back where you came from. So we get stuck there. So now we go out here, we go out here. We get stuck, so we have to start backing up. And we back up all the way to the start. Now, what can you say about the length of that yellow tour?
It's 2 times the minimum spanning.
Right, it's twice the length of the minimum spanning tree. So the yellow tour is twice the length of the minimum spanning tree because we used every edge twice. Okay. Now I'm going to erase the minimum spanning tree. Now what we're going to do is we're going to fix up the tour in a certain way, and I'll just explain as we go along rather than try to explain in advance. So I changed that edge to purple. So we're tracing the yellow edges. And if we ever get to a situation where we are coming back to a place we've been before, what we do instead is go to the next city directly, the next vertex directly. Okay, see what I did? Instead of going E to D to A, we go from E to A. Okay? Now, what can you say about that purple tour now? The fact that we've shortcutted, is that a shortcut? Going from E to A directly instead of E to D to A?
Yes.
How do you know it's a shortcut?
The triangle inequality.
That's where the triangle inequality applies. So that shortcut there has got to be better than what the original yellow route. So we go here, we've been there before, so there's our shortcut. We go there, and at this point, we're going back, and so we tried it. The shortcut from we would consider next is F to C, but we've been to C. Then we would try F to D. We've been there, F to G, and so on. And in the end, we just come to here. So now we have constructed. That is actually a Hamiltonian cycle. Okay.
Isn't there like a better solution?
Yes.
Are you assuming these purple edges exist in the graph?
There's an edge between. We're assuming there's an edge between every pair of vertices. Yes. You're not raising your hand.
Oh, no.
Okay. Yes.
Better solution to go from G to E, then E to D.
Okay. So is there a better solution? There may well be. Remember, we're after an approximate solution. So I'm not claiming this is the best solution.
So could we apply another approximation?
So what we want to do is see what kind of bounds can we put on. How good is an approximation? How bad can the approximation be? I mean, again, we assumed there was a vertex between an edge between every pair of vertices. So it's nothing to brag about that we found a cycle. The cycles are easy to come by if the graph is complete. So what I want to get at is how good or how bad is this approximation? I mean, what Anthony just suggested is, it looks like we can improve it by going from G to E to D to A. That sort of looks shorter to me too. Okay? But let's see how bad it is. Okay, so now I have the minimum spanning tree drawn, and I have the purple edges drawn. And the yellow edges I took out. Remember the yellow tour was the one that followed every white edge twice. So TSP, let's let that stand for the cost of the optimal solution. And I don't know what it is, but there's an optimal solution somewhere. We'll call that TSP. MST, we'll let that stand for the cost of the minimum spanning tree, the white edges add up to MST. And tour, that is an actual tour that we found. That's the pink edges up there. First thing I say is that 2 times MST equals cost of yellow. Remember, yellow is related to the white edges because the yellow visits every edge twice. So obviously, since the yellow just traverses every white edge twice, it stands to reason that 2 times the MST, which is the white edges, is equal to the cost of the yellow edges, which, just to remove the clutter, I haven't shown up there. Okay, you buy that? This says that TSP is greater than or equal to MST. Okay? Why is that? How can we say that TSP, which is the optimal solution, is greater or equal to MST, which are those white edges up there? Yes, Anthony?
Because the TSP has to have like 2 more edges than the minimum spanning tree.
Okay, he said the TSP has 2 more edges. I think it's 1 more edge.
Or 1 more edge.
But here's the way to think about it. MST, minimum spanning tree, connects every vertex. Connects them all together using D minus 1 edges, and it's minimum. Now, the traveling salesman problem graph, the Hamiltonian cycle problem that's found, has 1 more edge. Take one of them away, and what do you have? Take one of the edges away from the TSP solution. What do you have? I have a spanning tree. Right? If you take any edge out and break the cycle, you still have a set of edges that connect all the vertices together. You've just taken out the one that closes the loop. So if you take that edge away, you have a spanning tree. That spanning tree can't be smaller than the MST. And then we're adding that edge back. So when I say that adding that edge back will make the path longer, which makes me think of what you said about negative edges. So this proof here is assuming there aren't any negative edges. I didn't state that, but I realize it's an implicit assumption.
You said it's greater than or equal to?
Mm-hmm.
So one would be equal to, is that like 2 vertices on top of one another?
Okay, so he's asking when would TSP be greater than or equal to MST? I guess it couldn't be. It would always be greater than it because there's always that extra edge, as long as the edges are positive, which I believe I have to assume here. Yeah?
Would it though, because I figured, because with the triangle inequality, one of your edges could be shorter, right, than the 2 combined.
Well,
But
no.
you have 2 different edges though.
Let's assume that, just so I don't have to draw anything else, let's assume that this pink cycle is the solution to the traveling salesman problem, the exact solution. Okay? If I take this edge out or this edge out, and you're going to have to read them as, forget the arrowheads, imagine that they're undirected edges. Suppose I take this pink edge out. What I have left is a spanning tree. Right? Everything's connected together. That spanning tree has to be greater than or equal to the minimum spanning tree. And then to obtain the cycle, I'm actually adding an edge back. That's not going to make it smaller, it's going to make it bigger. So, yeah, the triangle inequality doesn't help us there. This is going to be greater than MST. And as a result, it's also greater than or equal to. Yeah?
What if you have one node and one edge itself not being equal to?
So a graph with one vertex?
Yeah. And then edge to itself.
Yeah. I mean, I'm just debating what would be. I think for one edge, for one vertex, I think the solution is just no
spanning tree.
No spanning tree, no cycle. Just the vertex by itself is the.
You can only visit each vertex once. If you go along the edge, then you visit it twice.
So yeah, certainly that's an extreme case. But if we've got more than say two vertices, it's easy to see this. Okay. So anyway, TSP is greater than or equal to MST. And then I say 2 times MST is greater than or equal to that peak tour. Why is that? Yeah?
Because 2 times the MST is traveling along the MST twice, whereas if the triangle inequality holds, then each edge that you used instead of traveling back along the same edge is shorter.
Okay. So right here, 2 MST is equal to the cost of yellow. Remember the yellow path was one that followed this by visiting, it traversed every white edge twice. The pink tour is an improvement upon that yellow tour. And so, whereas 2 MST was equal to the cost of yellow, since that was true, 2 MST is going to be greater or equal to the pink tour. And that's a triangle inequality where pink tour is shorter than that yellow tour. Then we just put that all together. 2 this taken together with that, TSP is greater or equal to MST, so 2 MST is still going to be greater or equal to the tour. So 2 times the traveling salesman problem is greater or equal to the tour, which means that the traveling salesman solution is greater than or equal to a half tour. Anyway, we're off by at most a factor of 2.
So what would show the worst case?
What would show the worst case? Okay, so he's asking you to construct a situation where we achieve the worst case, and I'm not prepared to do that. I haven't thought of that hard enough, so I don't want to flounder around. But just these inequalities I'll put together tell you that if you use this approximation algorithm, you'll be within a factor of 2 of the optimal. You won't be more than 2 times more than the optimal solution. In this case, I think we're a lot closer. Right. Yeah?
Can you please explain the 2 MST is greater or equal to tour again?
This here?
Yes. Can you explain?
Okay. So 2 MST is greater than tour. So what's MST up here? Okay, it's the white. So let's back up to where I have the yellow on here. Okay, so first thing I observe here is that, so the yellow tour is equal to 2 MST, right? So 2 MST is equal to the length of the yellow tour. Now, what's the relationship of the pink tour to the yellow tour? So I'm going to convert this into the pink tour. That makes so the pink tour is shorter than the yellow tour. So if 2 MST was equal to the yellow tour, and the pink tour is even shorter, 2 MST is going to be greater or equal to the pink tour. Any other questions? All right, so this is just an example of an approximation algorithm, but you can't use it unless the triangle inequality is observed. And this is what we talked about, why there's not an approximation algorithm to the general problem, because an approximate solution to TSP is still an exact solution to the Hamiltonian cycle problem. And that's NP complete. Right, now, that's an example of an approximation algorithm. So you can characterize approximation algorithms by the approximation ratio, which you get by, it's the ratio between the optimal solution and the approximation. And we always do the division. It depends if it's a min or a max problem. You still do the division, so the ratio is always greater than 1. So that's why I show the denominator. I show the division both ways. Okay, so you're sort of looking for the worst case approximation and dividing it by the optimal solution. Yeah.
I'm confused because you said that every approximation to an NP complete problem is still going to be NP complete.
No, I said that for traveling salesman problems. I didn't say that some NP complete problems have approximation algorithms. The traveling salesman problem doesn't, but some NP complete problems do. So in the case of traveling salesman problem, what would the approximation ratio be? The ratio between the, what you claim to be an approximation algorithm.
2.
Well, the approximation ratio is 2 for the special case the triangle inequality holds. What if the triangle inequality doesn't hold? Yeah?
So it'd be like twice or the sum of all the biggest edges in the graph.
Well, but in the what we want to take is the worst case approximation. So some graph that has the worst case approximation divided by the optimal solution. What bound could you put on that? Assuming P is not equal to NP. Yeah?
Is the graph complete like we were beforehand? So we
No, we're not assuming the graph is complete. We're not assuming it's triangle inequality, just in general. Yeah?
Guess an n squared.
No, n squared would be an approximation algorithm.
Would it be undefined?
It would be infinite. There is no approximation algorithm. So you can't have a finite approximation ratio.
So what would the optimal be if there's no solution?
I didn't say there was no solution. I said that there's no approximation algorithm. If there's a finite approximation ratio, if you can guarantee, if you've got some bound where you can guarantee that the error is bounded between the approximate solution and the real solution, then that means there's an approximation algorithm. There's not for TSP. So you can have a hierarchy of ratios. So you can have sort of the infinite ratio. There's no finite approximation. That's TSP. You could have a fixed lower bound. So you could have a constant ratio. So TSP with the triangle inequality, approximation ratio is 2. The ratio between the approximate solution and the exact solution will never be bigger than 2. So that's an approximation ratio of 2. Set cover problem turns out to have an approximation ratio that's approximately log n. So it's not a constant ratio, but it's a function of n. We'll look briefly at that in a second. And for the knapsack problem, which is NP complete, you can get an approximation ratio arbitrarily close to 1, which is pretty good. So it's a polynomial time approximation ratio that will get you, you have to spend more time at it, but if the amount of time is not exponential, you can get as close to 1 as you want. So this is sort of the best case approximation ratio as long as P is not equal to NP. TSP is the worst case, and there are things in between. So here's a set cover problem. You're given a set and a collection of subsets. So for example, here's the set. These are the 3 subsets. And your job is to find the smallest collection of subsets whose union equals the set. So what's the solution here?
S1,
What's the smallest collection of subsets that covers the set?
S1 and S2.
Yeah, you take S1 and S2 together, that'll give you B. Okay? Easy to solve in this case, but it's an NP-complete problem. Turns out the greedy approach doesn't work. I think we talked about this once before. The greedy approach would be always pick the set that covers the most uncovered elements. So the greedy approach would say, pick this one first, because that takes care of 4 elements from B, leaving only 2 to take care of. But if you pick this one first, you're still going to have to take both of those to get the 1 and the 6. And I won't go into the details, but the approximation ratio is less than the natural log of the size of B. So the greedy algorithm gets within that factor in the worst case. So I haven't explained much about it. It's just an example of what can happen with an approximation ratio. But I do want to spend more time on the knapsack problem. Because people look at the knapsack problem and they say, well, we have a dynamic programming solution for it. Why is that not polynomial time algorithm? And just let me explain why. Take this instance here. Okay? Pretty small problem, right? In terms of number of bits it would take to describe this. It would take some bits to describe this table, so we'll assume there are n elements here. So the size of the problem is going to be, the size of that is n, O of n. And there's a few bits more, but they're not going to be bigger than n. But how big of a table are we going to have to use to do dynamic programming on this? Do you remember what was the height of our table?
This is the capacity.
Well, the height of the table, and so when we did it before, the x-axis had to go from 0 up to the capacity. So we had, in this dimension, we went from 0, 1, 2, 3, all the way up to that number. The height was something like n plus 1. So the height is proportional to the size of the input. The width is all out of proportion to the size of the input. Because it just takes a few bits to describe that number. You know, like, what is it? Is that 1? It's 9 billion. So it's going to take 33 bits to describe that number. But the table itself is gigantic. So a relatively compact problem with that gigantic table to fill out. The table is exponentially larger than the number of bits required to describe all this stuff. That's why it's, even though there's a dynamic programming solution, the problem is the table is exponentially large. So filling out that table will take effectively forever. So, how can we speed this up if we're willing to get an approximate solution? I mean, what's the fundamental problem here? I'll let you chew on it for a minute. How can we tame this? Do it with less space. Yeah?
I'm currently worried about ratios. So the knapsack problem could be really hard if you had a small knapsack, but I feel like if you had a knapsack that could carry 1 trillion pounds of stuff, you'd expect most of that to be the item that has the greatest value weight ratio.
Mm-hmm.
So you could just worry about the ratios and.
All right, so he's proposing that we figure out which of these gives you the most bang for the buck. We take a bunch of those, and then worry about optimally filling the remainder. Okay? That's one approach we can take. It's not the one I'm going to show here, but that's the idea behind an approximation algorithm. It's doing something to get the table smaller. Yeah?
You take the most significant values of the numbers?
Yeah. Scale everything down. Look at all the precision in here. What if we just divided every number, every weight, every value, every capacity by 10 to the 5th? Just lopped off the last 5 digits and solved that problem.
A lot smaller.
Okay? So if we're careful about how we lop off the last 5 digits, we're still going to get a legal answer. It might not be optimal, but maybe it's going to be close. So let me show you what I mean. All right, that's going to be a big cache. Now, when we do the division, let me go back to this. when we divide the weight, we're going to divide the weight by 10 to the fifth. So we're going to remove the last 5 digits. Should we round down to 18 or up to 19 when we do the weight? Right, we want to assume the worst. We want to make sure our solution isn't bigger than the actual capacity of the knapsack. So we'll round the weights up. Okay? What should we do about the values? Turns out we want to round them down. So we want to guarantee we're doing an underestimate, not an overestimate. So we'll make the weights bigger. We'll make the value smaller. We'll make the capacity smaller. We'll round down. So let's go do this. Okay, that's what we just said. So there's that, and there's divide by 10 to the fifth. There's a simplified problem. We get 19 because we rounded up for the weights, and we do that consistently. The values get rounded down, and the capacity got rounded down. Okay, that's a much more manageable table. Now the table just has, just shy of 93,000 entries. Still fairly large, but a lot smaller than our million entries. And our numbers are smaller. So it turns out, if you take that and you actually solve it, these are the two solutions. I solved this exactly using the dynamic programming algorithm. It took a while, but this is the exact solution. This is the solution you get if you solve that problem. And the thing to notice is how different they are. This one said, take no A's for some reason. This says take 1. This said take 1B. This said take 1,104. This one mainly takes C's. Okay? Now, how bad do you think is our approximation? How can we figure out how bad the approximation is? Yeah?
Multiply the approximation on the right by 10 to the fifth, and then divide it by the actual solution?
Yeah, we need to figure out, first of all, okay, this one's still a total of whatever that number is. 806 million. We need to figure out, take this solution, take this exact solution here, the 1, the 1,104, and so forth, and recompute using those values up there. See what they were worth in terms of those values. And so if you do that, there's the solution. That's not right. Okay. That's the solution. This is the new table. So here we got this total by multiplying the value of A, which is 1 by 1, and 7 by 1104. For this one, we're taking 1A and multiplying it by 109235, and we're taking the B, 1104 B's, and multiplying it by 728292. When you do that, you get this. So the optimal solution was you could steal 806 million plus a little bit worth of stuff. The approximation is 804 plus a bit. So the ratio in this case is 1.0015. So we didn't get the exact solution, but we got close. Yeah.
Still 2 million off, though.
Yeah.
Depends on how.
Right. Right. But it turns out that what would we do to get a better approximation? Divide by 10 to the fourth. So now it's going to take longer, but still, longer than the divide by 10 to the fifth, but it'll get you close. Yeah.
Well, how much faster was it in seconds to do 10 to the fifth? Is it like a huge time savings, or?
Well, okay, so let's see. In the original version, we have a table that is about 10 billion entries. This new entry has 10 to the fifth fewer entries. So it's 10 to the fifth faster, 10,000 times faster. No, 100,000 times faster. 10 to the fifth. Is that right? Yeah. 10 to the fifth is 100,000. So it's 100,000 times faster. Okay? Yeah?
How long did it take you to run the?
Yeah, I did it more than a week ago. I don't remember. I did it a year ago. So. It wasn't like heroic. It didn't take it wasn't like it took days or anything. It probably took many minutes. Okay? so that's just an example of an approximation ratio. I mean, of one that you get actually pretty close. It turns out that if you pick the epsilon, you can pick an epsilon such that your approximation ratio is arbitrarily close to 1. It just corresponds to how you round. Okay, so that finishes just some quick examples of what approximation algorithms are like. Yeah?
How do we know that TSP doesn't have an approximation algorithm?
Because if it did, so he's asking, how do we know that TSP does not have an approximation algorithm? If it did, we would use the following algorithm for a Hamiltonian cycle. Someone gives us a graph and says, does this have a Hamiltonian cycle? Okay? Say it gave us an unweighted graph. Is there a Hamiltonian cycle? Or find the Hamiltonian cycle. That's a cycle that hits the vertex once and goes back to the beginning. So we would take that graph, we would add weights to it, we would call the TSP approximation algorithm. It would give us back a crappy approximation. We don't care how bad. We would take the approximate cycle that it gave back, remove the weights. That's our solution to the Ham cycle problem.
Why would that be bad?
We know the Hamiltonian cycle problem is NP complete.
Okay, so NP complete. Okay, so how do we know that the Hamiltonian cycle problem doesn't have an approximation? Is that because...
Well, the Hamiltonian cycle doesn't have an approximation algorithm because it's not an optimization problem. You can't approximate the Hamiltonian cycle problem. The point is, the worst approximation to traveling salesman, the approximation to traveling salesman problem would not be an approximate cycle. It would be a cycle. It just wouldn't have the minimum weight. It would be a perfect solution to the Hamiltonian cycle problem. So, if there is an approximation algorithm for the traveling salesman problem, then there is a fast way to solve the Hamiltonian cycle problem, which would mean P equals NP. So if P is not equal to NP, there cannot be an approximation algorithm for TSP. Because then we could solve Hamiltonian cycle. Any other questions? Yes?
Seems strange to me that the knapsack problem is NP complete, but we can get an arbitrarily precise solution in polynomial time.
Okay. It's not a question.
You're right.
Does it seem weird to me? Maybe that's a question.
Does it seem weird to you? Or can you
Yeah, I mean, the difference is the knapsack problem, the source of its NP completeness has to do with the amount of space it takes to encode numbers. And so the knapsack problem is in a class of problems that would not be considered NP complete if you wrote the numbers in unary. I think we've mentioned that before. If the space it took to write a number was proportional to its magnitude. So just imagine if Roman numerals were the only letter you got as I. So 100 is written with 100 I's. So if you use that numbering system, then suddenly the size of the table in the dynamic programming solution is proportional to the size of the input. And suddenly it's not an exponential algorithm anymore. So I don't know I don't know how that relates to approximation algorithms in general, but that's sort of how I think about the big difference between knapsack and the other problems. The knapsack is the kind of problem that I have a hard time convincing students requires exponential time. Yeah.
All NP problems, NP complete problems can be reduced to other NP complete problems.
Yes, every NP problem can be reduced to every other NP
So why can't we just take the Hamiltonian, the knapsack problem approximation and then reduce that to an approximation for any NP?
Well, the fact that you can reduce one problem to another doesn't say anything about approximations. It doesn't imply that if you do the reduction that that the approximation will be, the resulting approximation.
Yeah, so you just massage the input and the output, right?
What's that?
You just tailor the input and the output.
Yeah, we can certainly do the reduction, but that doesn't mean that, it doesn't imply anything about approximations. It's a nice idea. Yeah?
Sorry, I want clarification on the definition of approximation algorithm. Is it, do they run it in polynomial time? In
Yeah.
order to be, so they have to run a polynomial.
Yeah, to be considered an approximation algorithm, it needs to run in polynomial time. The other reason, I think I give you a better answer about the approximation deal. Technically, the traveling salesman problem is not NP complete. Okay? Because it's not polynomial time verifiable. Right? The Hamiltonian cycle problem is NP complete. And I argued previously that there's really nothing to be gained by stressing too much about the difference between a search problem and an optimization version, because you can easily, if you can solve the search, you can solve the optimization. But if you want to be technical about it, TSP is technically not NP complete, simply because there's no fast way to verify the answer. Yep?
Well, that's why you have kind of the complementary spaces to NPs. You have the FNP function, the space of NPs, basically function problems instead of decision problems. Then you have NPO, which is the space of the corresponding optimization problems.
Okay. Traveling salesman problem is NP hard. NP hard just means at least as hard as an NP complete problem.
Well, there's the decision version, right? That isn't.
So, I mean, I don't want to, I'm happy just to understand NP and NP complete. NP hard is easy. That's just, if you have a problem to which all other problems in NP reduce, that problem is NP hard. It's at least as hard as any NP complete problem. To prove it's NP complete, remember there's an additional step. You have to prove that it's NP hard via reduction. You also have to prove that it's a member of NP by showing the verification algorithm. So NP completes the intersection of NP and NP hard. Yeah?
So do you have other examples of problems that are in NP hard but not in NP?
Problems that are NP hard but not in NP? The halting problem, certainly.
So you can reduce all of NP into the halting problem?
I believe so, yeah.
How do you do that?
I don't know how you do that. I can think about it. Okay, so there's obviously, you could spend your lifetime exploring these issues, and some people do. You're getting a little bit of a taste, though, this week of what algorithm research is like. Because all the other CAS problems I've given you, I've also given you an algorithm. You're just implementing the algorithm. Here, you're doing essentially a little bit of research, trying to find a way to solve the problem. If that sort of thing really excites you, if you really enjoy that, you might think about taking other algorithm problems or going to grad school and studying algorithms or whatever. Yeah?
So is there a class called approximations?
No, there's no class called approximations. There's an advanced algorithms class. Beyond that, you essentially, the way you learn about algorithms is you enter into an apprenticeship with a faculty member, say, that does research in algorithms. That's called grad school. It's called getting a PhD.
For most of this academic year, I looked forward to the CS4150 lecture on April 21st because I knew it would be the last one of my career. From time to time, I would think about what I was going to say in that lecture, but after spring break I stopped because the lecture was already on YouTube. I want you to stay healthy over spring break as you travel. Be sure to wash your hands because I want to see everybody back here in 12 days. Things didn't quite work out like I had thought, and I still haven't seen any of you in person, but my advice is still sound. Stay safe.